Good afternoon. I'm Sarah DeWitt from the Office of Public Affairs at NASA's Goddard Space Flight Center in Greenbelt, Maryland. I'm pleased to introduce the second of today's 3 briefings, which will focus on the science of glory, a mission that will improve our understanding of aerosols and solar irradiance and their effect on Earth's climate. On the panel with me today are 4 principal members of the GLORY science team. Our first speaker will be Hal Mehring, GLORY program scientist from NASA headquarters in Washington. Our second speaker is Michael Mashenko, GLORY project scientist from NASA's Goddard Institute for Space Studies. Our third speaker is Greg Kopp, the Total Irradiance Monitor instrument scientist from the Laboratory for Atmospheric and Space Physics at the University of Colorado in Boulder. And our final speaker is Brian Cairns, Aerosol polarimetry sensor instrument scientist from NASA's Goddard Institute for Space Studies. We'll go ahead and start with Hal Mehring.
Thanks, Sarah. We're really happy to be here today. It's been a long road with a few potholes, but now we're very much looking forward to successfully launching GLORY. Now, we know the Earth's climate is changing, and we know that the majority of that change is caused by human activities. The grand challenge that climate scientists now face is to predict when and how much climate will change with enough fidelity to provide policymakers with reliable information that they need to formulate policies that avoid catastrophic climate change without unnecessarily damaging people's lives. Climate models are the tools needed to forecast climate. The value of the measurements to be made by the GLORY mission are the improvements in climate models that data will enable. Now, the sun provides the power to the engine that is our climate. GLORY will make 2 kinds of measurements using 2 sensors focused on different aspects of the sun's energy to help us better understand Earth's climate. The first sensor, the Total Irradiance Monitor, will measure the total amount of energy coming from the sun to the Earth. The TIM will measure watts per square meter of solar energy coming to the Earth with significantly improved accuracy, precision, and stability. The GLORY TIM will continue and improve our current 32-year record of total solar irradiance. The second instrument, the Aerosol polarimetry sensor, or APS, will measure properties of sunlight reflected from tiny particles called aerosols suspended in the Earth's atmosphere. The properties of this reflected light are related to the characteristics, the properties of those atmospheric aerosols. Both natural processes and human activities produce these aerosols, and these aerosols affect the Earth's energy budget climate in a number of ways. For example, aerosols can scatter and absorb light. Higher concentrations of reflective aerosols cause more scattering and can cool the whole Earth system. Higher concentrations of aerosols with color, like soot or black carbon, can cause atmospheric heating and cooling of the surface below. Aerosols also affect the radiative properties, the reflective properties of clouds. The effect of aerosols on climate is very complex, and it is the greatest uncertainty in our ability to predict climate. GLORY APS is aimed directly at this very important problem. The Earth's climate system is complex and integrates land, ocean, atmosphere, and biological processes on a global basis. In order to put GLORY measurements in a multidisciplinary global context, GLORY will orbit the Earth in the so-called afternoon or A-train. With GLORY, the A-train will be a constellation of Earth-observing satellites orbiting in close formation to provide coincident, comprehensive, and coordinated observations of the Earth system. Sarah?
Thanks, Hal. Our next speaker is Michael Mashenko, the GLORY project scientist from the NASA Goddard Institute for Space Studies.
Thank you, Sarah. First of all, I would like to join Hal and say that it's really exciting to be at this time here when a new scientific phase in the GLORY mission is about to begin. My graphic shows the overall scientific objective of the GLORY mission. As you can see, the Earth's climate system is fueled by the incoming solar energy. Part of this energy is reflected back into space, and Earth also emits some heat energy. If the incoming solar energy is perfectly balanced by the outgoing energy, then the climate system is expected to be stable and not change. But if there's a disbalance, for example, if the amount of the incoming energy exceeds the amount of energy going out, then the Earth's climate system is expected to change. As we have been observing for the past 50 years, it is warming. This tells you that it is extremely important to know how much solar energy is entering the Earth's climate system, and the objective of the total solar irradiance monitor on the GLORY mission is to measure this incoming solar energy with extremely high accuracy and stability, and in fact to continue the 32-year uninterrupted record of solar energy measurements from space. Once the solar energy enters the Earth's system, it gets reprocessed in several ways. It can be reflected back into space, or it can be absorbed in the atmosphere and at the surface. And a very important role in this redistribution of the solar energy is played by tiny particles, which are airborne. They're called aerosols. Most of them are so small that would be invisible to a naked eye, and yet there are so many of them that their effect on climate is estimated to be quite significant. The problem with these particles is that they can be natural as well as man-made. So we need a global understanding of the distribution of these particles and of their composition. This can be done only from space. My next graphic is an animation, which was created using a theoretical computer model of aerosol transport. In this case, being transported is tiny soot particles. So we have these theoretical tools how to evaluate the transport of aerosols. And yet we know that these theoretical tools are still not accurate enough. The accuracy must be improved quite a bit for us to better understand the climate and predict the future climate. Again, this can be done only from space, but it's not easy because the aerosol particles come in all shapes, sizes, and compositions. And different types of particles can coexist. So this really calls for a very special satellite instrument capable of addressing the aerosol problem with the requisite accuracy and specificity. And in fact, the GLORY APS, the aerosol polarimetry sensor, is the first instrument of its kind. It will measure not just the reflected intensity or brightness of sunlight, but it will also measure its state of polarization. It will accumulate 250 views of the same piece of real estate from space, and it will do that in 9 spectral channels. So it will provide a wealth of information, measurement data about each scene it's going to look at, and we expect that this wealth of information will allow us to determine the properties of aerosols and the underlying surface, as well as clouds, with the requisite accuracy. My next graphic shows you that the GLORY spacecraft will become part of the so-called afternoon constellation of satellites. It will be the 6th car in this A train. And for the team instruments, it doesn't matter how we fly the spacecraft because all it does is to look at the sun at all times. But for the GLORY APS, it is quite advantageous to be part of the A train because different satellites in this A train carry numerous instruments looking at the same scenes underneath at about the same time, and they provide a detailed view of the climate system. The addition of the APS is expected to provide even a more comprehensive view of the system. By combining measurements from APS and other instruments, we will be able to say much more than we would otherwise using these instruments separately. I'll give you just one example. APS will be flying right behind the Calypso LiDAR. And the LiDAR is a very capable instrument using a very powerful laser. It can determine the vertical profile of the aerosol composition in the atmosphere with very high accuracy. On the other hand, it doesn't have this exquisite sensitivity to the microphysical properties of particles as APS does. And by combining the measurements from APS and from Calypso LiDAR, we will determined for the first time the vertical distribution of the microphysical properties of aerosols, and this is extremely important to improve our understanding of the climate system. Back to you, Sarah.
Thank you. Our next speaker today is Greg Kopp. He's the Total Irradiance Monitor Instrument Scientist from the University of Colorado at Boulder's Laboratory for Atmospheric and Space Physics.
Thank you, Sarah. So the Total Irradiance Monitor on GLORY is looking at the sun. And the reason is that the sun's providing all the energy input, essentially, that's driving the Earth's climate system. We'll look at the sun in a minute. If you could please start rolling the first animation, but let's not go to it just yet. The sun's providing all the energy input to the Earth's climate system. It's providing 10,000 times as much energy as the next input energy source, 4,000 times the amount of energy of all the other input sources together. Now this animation shows in the blue line here, which incidentally is taken with the predecessor to the Total Irradiance Monitor that's going to be flying on GLORY. This one's flying on NASA's SOURCE spacecraft. Blue line is showing variations in TSI, or total solar irradiance, the total amount of energy coming from the sun that's heating the Earth's climate system. And you can see that it varies. Here, with the passage of a large sunspot region and the formation of another one, as solar activity changes, the total solar irradiance, the amount of energy we're getting from the sun, varies with time. Now these are fluctuations that are on the order of 0.1 to 0.3%, and they're occurring over days to weeks. This entire animation here lasts about 3 months. The Earth's climate system doesn't really respond that quickly to these fluctuations. What we're more interested in is long-term. How does the sun vary? Knowing that it changes this much on short time scales, we'd like to know over decades, over centuries, how does the sun vary? Because those are time scales that can be influencing climate. That also means that you're going to need a long-term record of what the sun is doing. It's got to be extremely accurate. Being able to measure climate drives real stringent requirements on accuracy and stability of these measurements. Now, NASA, NOAA, and the European Space Agency, if we could go to the next graphic, have acquired a 32-year record that scientists now have, taken by several different instruments. The dozen or so instruments that contribute to this total solar irradiance record shown here are shown in different colors. You'll immediately see that each of the instruments is following the same behavior in the sun, kind of a gradual 11-year cycle where the sun will get a little brighter and a little dimmer. It also has these very short-term fluctuations that I showed you. Each of these instruments measures those same variations very well, but you'll see that there are offsets between each of these instruments, and those are due to calibration differences, something that we're aiming to be improving with GLORY by having an improved, accurate instrument. But it's been because of overlap of each of these instruments and each of these measurements, where following instruments will overlap with their predecessors, that you can offset each of the measurements shown in this plot, as we'll see in the next graphic, to form one continuous record of what the sun is doing over time. And it's from this continuous record, how the sun is varying and how that correlates to temperature changes on the Earth, that we can infer the climate sensitivity of the Earth to solar influences. So GLORY is now going to be continuing this record. It's very important that we have this overlap with preceding instruments and preceding measurements. GLORY is going to be continuing this record into the near future for us, following on to the Total Irradiance Monitor currently operating on SOURCE. So we'll be extending this record with time. We'll be improving the accuracy of this record, and that will take care of some of the offsets that I showed you in one of the previous plots, improve the record by not having those offsets. That mitigates a little bit against a potential future data gap. If we were to have a gap in data and come back with a following instrument and it reads a little bit higher or a little bit lower than what we'd seen before, is that due to the sun changing or due to an instrument change? By having improved accuracy, GLORY is going to be improving on that record and making it a little more robust against gaps in the data. So there are basically four things science-wise that we're looking to get from GLORY. We're looking to know what the true total solar irradiance value is on an absolute scale. By extending the record, we're going to be able to better tell what solar features are causing variations in the sun's output. We want to know, again, by lengthening this record, how the sun changes over decades, over centuries, And this extended record will then tell us with better certainty how the sun is contributing to climate change on the Earth and how sensitive the Earth's climate system is to solar inputs. Thank you, and back to you, Sarah.
All right. Thanks, Greg. Our final speaker on the panel today is Brian Cairns. He's the Aerosol polarimetry sensor instrument scientist from NASA's Goddard Institute for Space Studies.
Good afternoon. Thank you, Sarah. For some people, it's been a long road to get this Glory mission, but for me, this started before dawn in April of 1998 on a mountain above Santa Barbara, when we made the first measurements with an airborne prototype of the aerosol polarimetry sensor. And it was those measurements that convinced us that we could make measurements in the real world that were just as accurate as the ones we made in the laboratory. So I've not actually come very far, but it's taken a while to get here. So the reason I was up on this mountain before dawn is that I was setting up a sun photometer to make measurements of these little airborne particles called aerosols. Sun photometers look at how much the sun is dimmed by the little particles and are a really good way of making that kind of measurement. The reason that we can't use sun photometers to do the job that the APS is going to do is that you'd have to have 500,000 of them uniformly distributed around the world, and it's kind of awkward to stick them in the middle of the southern oceans. Can I have my first graphic, please? So what the aerosol polarimetry sensor will do in the afternoon constellation is we'll have 600,000 observations spread around the globe, and at each one of those points we take 10,000 measurements. And the reason that we take 10,000 measurements is because aerosols and clouds are kind of a mess. If you look at the graphic, this is a picture of the Pico de Orizaba, which is the highest mountain in Mexico. And on the left, you can see pollution flowing out from Mexico City. And on the right, there are cumulus clouds in the coastal range. And so, as Greg said, the sun is the thing that's heating the Earth. It's the dominant source of energy coming into the system. And what APS tells you is what energy is coming back out. But more than that, it tells you what is coming out and what caused it to come out, because you really want to know whether you have these little particles that are going to absorb light, sending it back to space, because they'll send it back to space but also absorb in the atmosphere, or if it's something like a cloud which doesn't absorb very much, so you reflect it out, so there's not much absorbed in the cloud, and it gets to the surface and heats the surface. And the way in which we diagnose whether we have small aerosol particles, big aerosol particles, non-spherical particles, ice particles, or cloud droplets is primarily using the polarization. Could you show the next graphic, please? This is sort of the most obvious and visually enticing example of polarization. On the left is a picture taken. It shows a rainbow, and a polarizer was used so you can actually see that rainbow. On the right, there's no rainbow because there was no polarizer used, and the reflected light is so bright that you simply can't see the rainbow without a polarizer. Why do we want to measure things like rainbows? It's because the angular distribution and color of that light tells you exactly how big those cloud droplets are, and it tells you what the width of the droplet size distribution is. And this kind of information is what we use when we're trying to diagnose whether aerosols have changed how those clouds are formed. Can we go to the next view graph, please? So we're interested in trying to understand whether it's natural aerosols or aerosols that we make that are dominating the climate signal. And obviously, when you take a picture of Los Angeles, it's really easy to know where the aerosols came from. We know that most of the ones over Los Angeles, they're ones we made. The reason that we have something like the aerosol polarimetry sensor making 10,000 measurements of these 600,000 points around the globe is to diagnose the composition of the aerosols in those locations so that we can distinguish between the contributions from natural sources of aerosols and anthropogenic aerosols. And can you show my last graphic? And then there's the cloud effects, and this is just a cartoon showing that every cloud droplet, every ice particle in a cirrus cloud forms on an aerosol particle. That's the energetically easiest way for them to form. So if you put a lot of little particles in the atmosphere and then you lift a parcel of air, then what's going to happen is you'll form more little droplets. And what that can do is it can make your cloud brighter. It can also mean that the cloud will last longer because it's less likely to grow large enough to rain out. And so, again, this is why we need the aerosol polarimetry sensor to do these very accurate measurements of the droplet sizes of droplets in clouds, and also understand how many aerosols were present and when the cloud was formed. So, to summarize, the aerosol polarimetry sensor were like 600,000 sun photometers spread all over the world, making 10,000 measurements at each point around the globe. And we're really trying to nail down exactly what the contribution of aerosols and clouds is to the amount of radiation that's reflected out of the atmosphere and how much gets to the surface. And back to you.
All right. Thank you, Brian, and thanks to each of our speakers today on this GLORY mission science briefing. At this point, I'm going to go ahead and take some questions. We'll start here with news media in the room, and then we'll go to the phones for questions from Kennedy. If you could state your name and affiliation when you get the microphone.
Janine Scully, Santa Maria Times and Lompoc Record. It's kind of been touched on, but we're writing for Joe Citizen. Can someone explain why Joe Citizen should care about this mission and what it's going to really bring to the teacher and the local schools or the farmer in the local fields?
Well, ultimately, it is about our climate, whether it changes or not. And to know whether it changes or not, we need to know the components of the energy that go in and go out with an extremely high accuracy, which at this point, we simply don't have that accuracy, except for the incoming solar light. We know that energy accurately, and we'll know that even more accurately as soon as GLORY is launched. But the ways energy is reprocessed in the atmosphere are so complex, and there's so many different mechanisms that affect it. We need to address each of these mechanisms separately, and APS will do that with respect to aerosols. So ultimately, it is about our lifestyle and the conditions in which we live and whether climate is changing and how accurately we can predict climate changes. And to do that, we need to know this energy budget equation with a very high accuracy, and without APS and team, we cannot do that.
If I could amplify just a little bit, as Brian mentioned, that aerosols do impact clouds, and one of the examples he used was that increased numbers of aerosols will create clouds with larger numbers of droplets that are smaller and less likely to precipitate. And so as climate changes due to increased concentrations of aerosols, you could see redistribution of rainfall or even reductions in rainfall, and climate models do indicate that. So something that farmers, for example, would be very, very interested in knowing about.
I guess the last comment I would have is that right now we don't really know what the effect of aerosols is on climate very well. It could be 50% larger or 50% smaller than the current best guess. And what the aerosols do is they mask the greenhouse gas warming. So depending on what you assume about aerosols, you can either have a very sensitive climate, and the aerosols are masking most of the greenhouse gases, and that will give you the right prediction of temperature over the last century. Or you can have a less sensitive climate and fewer aerosols so that the greenhouse gases are actually causing the same warming. So right now we have this big uncertainty in how sensitive the climate of the Earth is, and that's a big issue for the future, because if a given amount of greenhouse gases gives us a small change, then we're all very happy. But if it gives us a big change, then that's a problem. And right now we don't know what that sensitivity is, and the measurements that we're going to make will help to constrain and reduce that uncertainty.
And Janine, this also ties back to something that Hal said early on. We touched on, see, one thing GLORY does is it really spans kind of the anthropogenic or the human-caused reasons for climate change, but it also addresses some of the natural effects, the things that we have no control over, such as the sun. And as we try to set policy in the future, Joe Citizen pays Joe taxes, and as we try to decide what policies are going to be needed to mitigate or control climate change, we need to be able to distinguish how much of it we have control over versus how much we don't.
All right, I think we have another question here in the room.
I'm going to try my question again. Nora Wallace, Santa Barbara News Press. So in terms of understanding global climate change, can anyone rank Glory's importance in the A-Train constellation?
Well, maybe this question is a little unfair to all of these instruments.
We might be a little biased.
That's right. Just a bit. But for example, if you look at the forcings of climate, physical and chemical mechanisms that change climate, we can estimate them, and we did. And it turns out that the estimate of the aerosol forcing of climate is large. It's comparable to the forcing due to the greenhouse gases. But if you look at the uncertainty in this estimate, this uncertainty is as big as the estimate, which tells us that we don't know much about aerosols at all. And then if we look at the anthropogenic or man-made forcing of climate, it also has an uncertainty comparable to the estimate, and almost all of this uncertainty comes from aerosols, from the poor knowledge of aerosols. So it's difficult to overestimate the importance of the Glory mission, but it's not to say that we can underestimate the importance of the other components of the A-Train or other satellites.
And just to amplify, the value of Glory goes up substantially because it's in the A-Train. And as Michael indicated earlier, the combination of Calypso and Glory is much more powerful than either of those two alone. And add to that CloudSat and the Aqua satellite with MODIS on it. These are all really important and valuable data sets that when combined give us much more capability than any one of those would alone.
All right, I believe we have a question from the Kennedy Space Center.
Yeah, this is Denise Chow from space.com. My question is, it's a two-part question actually. How important is it that Glory will be launched at a time when the sun's activity is ramping up toward the solar maximum? And then second, with the 32-year record that we already have, what is already known about the correlation between solar activity and the concentration of aerosols in the atmosphere?
Okay, the first question is, how important is it that we're starting to monitor with Glory the sun as it's ramping up? That's not critically important. What is more critical is that we get very good overlap with the total irradiance monitor that's flying on source. So there's a good 32-year record that I've shown now, but it does rely on continuity and overlap of each of these instruments. The Glory total irradiance monitor has a better absolute calibration on it than anything that's been launched before. And by getting that instrument on orbit and able to overlap with the predecessors, we'll be able to link some of that historical 32-year record, tie it down better with better absolute accuracy via the Glory total irradiance monitor. So the criticality time-wise relative to the sun and the 11-year solar cycle isn't very important, but getting that overlap with the existing record, and particularly with the total irradiance monitor on source, is very important. In terms of links between the sun and climate, this is not directly addressing the aerosols yet. There are good correlations between solar activity and that 11-year cycle. We've been able to see about 3 of them so far with good spacecraft measurements. There are good links between temperature and solar activity. The links to aerosols are a little more tenuous and something that we will be improving a bit with Glory, but perhaps, Michael, you'd be able to say anything that you'd know about correlations between solar activity and aerosols.
Probably there's no direct correlation, but there was this global phenomenon called global dimming, which was occurring 20 years ago, which means that with time, the amount of solar energy penetrating all the way down to the surface was decreasing. And one of the hypotheses was that it is because the amount of aerosols in the atmosphere was increasing. And so they were reflecting more sunlight back into space just because of their numbers. And then this global dimming was replaced by global brightening, which is happening now. So more sunlight penetrates all the way to the surface and warms it. We don't know exactly what the physical mechanisms of these phenomena are, but no doubt aerosols contribute quite a bit to both phenomena. We need to study this phenomena, and also we need to study the human-made contribution to these phenomena. For example, there have been several laws adopted in the late 1970s in Europe and the United States, Clean Air Acts, and eventually they took effect, and we now know that the amount of aerosols over Europe and the United States has decreased quite a bit. Of course, this is not true of other parts of the globe, including China and India and other developing countries. So we need to know what these countries do to contribute to the aerosol population in the atmosphere and how this affects climate, and this is what the GLORY APS is going to contribute to.
Thank you, Greg and Michael. Do we have follow-up questions here in the room?
One more. I wonder if anybody would be willing to address what you think of having the hitchhiker payload going on your big career mission.
Good for them. No, it's been very carefully analyzed, and the risk to GLORY from their addition is negligible. So we're fine with it.
And they may be helping our future instruments because they're going to be improving perhaps communications that we'd be able to get from future spacecraft. So.
Can you characterize how much more improved the instrument on GLORY will be for measuring solar radiance compared to what you have been using before on SOURCE? Is there a way to characterize just how much neater and cooler this one is?
This one, the one flying on SOURCE, I should say, is about a factor of 3 better in accuracy than anything that's flown before. Now you notice, you probably remember the offsets on those graphs. The SOURCE being the newest instrument to be producing data for total solar radiance is a fair amount lower than the preceding instruments. And we'd spent quite a while trying to understand that and getting the entire total solar radiance community together. It sounds like a big community, but it's smaller than the group worldwide that we have in this room right now. But what we're learning is that an improved instrument design that we have with the total irradiance monitor that went up on SOURCE allows a lot less scattered light into the instrument. So the preceding instruments had additional light that made them read erroneously high. We recently got a paper published to that effect that explains the scatter and why those instruments read higher than the total irradiance monitor does. But it does look like the total irradiance monitor on SOURCE is at least a factor of 3 better than the preceding instruments. Now, with some design changes, mostly to the electronics in the GLORY total irradiance monitor, and with the new calibration facility that we've built under the GLORY program, partly because when I first started off on SOURCE, every time I would show that plot of all these offset instruments, someone would say, why didn't you guys calibrate these things? And it's not that simple. The offsets on there, they look large, but they're actually fairly small on the scale that's shown there. Every one of those instruments really is calibrated as well as people could do in the labs at the time. But there has been, over these 32 years, no facility on the ground that could calibrate one of these instruments end to end for measuring irradiance, something at solar power levels. On GLORY, we decided to address that problem, and we created a facility that would bring any instrument, any total solar radiance instrument in the world into our facility and be able to compare it against a NIST-calibrated cryogenic radiometer, kind of the gold standard in doing radiometry. So we created a new facility to be able to end-to-end validate these instruments, and the GLORY instrument is the first flight instrument to be calibrated on that facility. So not only have we improved the electronics and the calibrations of the GLORY TIM relative to the SOURCE TIM, but we've also kind of validated that with this good NIST-certified cryogenic radiometer and comparisons against that with the new facility. That gives about a factor of 3, or the combination of those two, the better electronics and calibrations, gives about a factor of 3 improvement over what we've achieved on SOURCE. So I am really looking forward to seeing GLORY go up and seeing it match very closely with the measurements that we're getting from the total irradiance monitor on SOURCE.
Thank you, Greg. We're going to go ahead and conclude this briefing now because we do have another one coming up shortly, and we need to make sure that we have enough time for all the questions on that briefing as well. So at this point, I just want to thank our panelists again one more time for being with us today, and all of our guests on the phone and here in the room. Stay tuned for the next briefing, which will cover the Alana mission, and we'll start momentarily.